Olá a todos, in this video I want to go over how to use the solver Percival with a LBFGS model. So if you don't know anything about it, I'm gonna quickly explain it, but you can skip ahead by looking at the chapters in the video. So first of all, Percival is a solver that was developed some years ago. It's an augmented Lagrangian solver using second order information, and internally it uses the solver Tron, which is a second order solver, but for bound constraint problems or unconstrained if you don't have bounds. The idea being that you transform the constraints into some kind of penalization, which is the whole idea of augmented Lagrangian. The question that sometimes we have is, what if I don't want to use second order information? What if I don't want to use the Hessian matrix? Luckily, Percival is a matrix-free solver, so it actually does need the product of a matrix times a vector, and because of that, we can use a LBFGS model modification on top of the problem that Percival is solving to make it available for Percival. So briefly going over Percival, so this is not an optimization problem that we have, a traditional one. This is the Rosenbrock problem with a constraint. So this thick circle, this is the constraint. So we just use the NLP model right here. The objective function is defined here in this line. This is the starting point. And then you have a constraint vector, right? This is a function. X goes into many things. In this case, a single constraint. And it's constrained between 0 and 0. So this is an equality constraint. So down here is just plotting, don't worry about it. If you want to solve this problem using Percival, you can just say output is Percival of NLP, and that will run the Percival solver in the background, and you can take that solution and plot it. And the way that we're going to do that is saying X is output.solution, and then you can just scatter the point X1 and the point X2, color red, size 3, and the solution should be printed here. So this is the solution that Percival found, which is the closest solution. Minus 1.2 is here, 1.0 is here, so the starting point is here. It's closest local solution. Let's say you don't want to use second order information. For instance, you can't or don't want to provide the gradient of a function. So we can do something like this. You have a function f of x, which is, again, let's just use the Rosenbrock function, why not? And you have the gradient, so you have something like my grad that computes the gradient of a function. So gx1 is 2 times x1 minus 1. Plus you have 8 times plus minus 2x1, so it's 16 times x1 times x2 minus x1 squared, and gx2 is 8 times x2 minus x1 squared. Okay, so you return gx as well, and you can create a manual NLP model by saying, hey, the help should also be useful here. So the manual NLP model, not the models. And by the way, I think I just call it NLP model because it looks nice. So the NLP model has a lot of options for what you can do. The basic one is you just have to give it a starting point. In our case, minus 1.2, 1.0, the function f, and then we also want to give the gradient. So here I am going to use grad equals my grad. And you can, if you call Percival here on NLP, by the way, it's an unconstrained problem yet, right? So if you call Percival here, it will not work. If you call trunc here, which is our unconstrained second order solver, it will not work. The function we call was not implemented, which the function we called is here in some place, hprod, which is the Hessian times a vector. If you call LBFGS, it should work because LBFGS only uses the first order information. So here, solution, oh, I forgot to get output equals output.solution 1, 1. right? So it does work if you only have the objective and the gradient. And this is just LBFGS, right? So this is just LBFGS for a problem that doesn't have hashing, that's fine. What we want to do now is to have constraints as well. So let's say you have a C of x constraint, x1 squared plus x2 squared minus 1. You also have to give the Jacobian, but you have to give the Jacobian vector product. So the Jacobian is 2 times x1, 2 times x2, which we could write as 2 times x transpose because it's a 1 by 2 Jacobian matrix. And the Jacobian vector product, so my J prod of a JV, x and v, is going to be JV is equal to J of x times v. And the function my JT prod, JTV, x and v, is going to be JTV is equal to JX times v. So by looking at this, it should be pretty easy to understand how to change this into an actual matrix-free thing. So like J of x is 1 by 2 times v. So this is actually 2 times x transpose times v. And JV only has one element, and that's it. For the other case is v should be a 1 element vector, so 1 only, and 2 times x times v1. And this should be a vector, so JTV dot equal, it still makes sense. So now I'm gonna say grad equals that, J prod equals my J prod, JT prod equals my JT prod. I should probably also use the exclamation marks in these names. And here return JV, return JTV for good measure. So all of these things are saying that I have constraints. I also have to inform here in my cons equals, and the cons needs the cons function. So here the constraint function and the lcon and ucon value. So the constraint function is C and 0, 0. And now that I have this information, I know this is a constraint problem. So LBFGS should only be called for unconstrained problems, and it doesn't work. So the basic idea is that this is a constraint problem, can solve it, but then I can call Percival to the rescue, but Percival can't solve it either. So why can't Percival solve it? Let's look at the error. I made a small mistake because, of course, this interface is for, you want to be more efficient, so you want to give the full vector. So we see x1 equals to this and not that one. And we can remove J of x. And I forgot about that. So now I'm here, my cons. So cons is my cons, exclamation. We can check again that my cons here, cons is a function of a cx and an x. So my cons exclamation is correct now. So now I'm having an error which is related to the function was not implemented. So it's the same error as before. We are trying to call a hashing for a function that doesn't exist. So what we're going to do instead is, instead of giving it the NLP directly, we can create a LBFGS NLP, which uses LBFGS model on top of it, LBFGS. And now this is using only these functions that are available to me, which means it's not trying to use the hashing at all. And you can check down here, the solution is shown, but you can actually print the output counters, or actually I don't need to print the output counters, just NLP counters. The NLP is the original problem, so NLP that I created just here right now, and I'm looking at the counters, so I'm looking at the number of function calls that we had, and you can see that we had 0 Hessian calls and we had 0 Hessian product calls, which means like none of the second order functions were called, which means that this is using only the LBFGS method. There is one little problem here though, we are not actually updating the LBFGS model. So the model starts as an identity matrix, maybe scaled, I don't remember, but it stays like that. So it does not improve. So it's a bad method. It's not second order, but it's not good enough. So what we can do is create a callback to update that. So the idea being that, so this is a callback for JSO solvers. You want to do something here that's gonna run at the end of the iteration. And the LBFGS model needs this call, which is the NLP has to be updated, and this NLP will be the LBFGS NLP, will be updated with the S and the Y, which are the, so X is XK minus XK minus 1, and Y is the gradient at these values, xk minus the gradient at xk minus 1, right? So this is what we have, or what we want actually. We don't have that yet. So we would like to have that. So how do we do this? So one simple way of doing it is by storing these values between iterations using the callback. So I'm gonna create something here. And I'm at the end of this, I'm gonna say, hey, this needs to be equal to solver X, and the gradient is going to be equal to solver GX. So these things are computed. They are XK and gradient of XK. But this is for the end of the callback call. And at the beginning of the callback call, what we want to do is, so if you already had one iteration, so these values at the end are already set, but they are equal to xk minus 1 and gradient of xk minus 1. You can say, hey, subtract the current x and then multiply this by 1. Right, so this is what you want. You can actually do this in a single line by doing it like this. Right? Yeah, this should be enough. And this should be solver gx minus y. And so now I'm getting the current xk minus the previous one, the current gradient at xk minus the old gradient at xk minus 1. And I'm pushing it into the model, which means that's going to be updated. I'm going to go up here and I'm going to press Ctrl S to save and run this so we can see a difference. And it's not running yet because I haven't changed the callback. That's a very bad thing. So now, yes, callback equals CB. Saving it, it's running, and you can see that it has made less iteration. Okay, and this works. And just to show that this method also works for larger scale problems, I have changed this to 100 variables, and I changed the Rosenbrock to a variation of it. That's essentially a bunch of Rosenbrocks unlinked. So for every 2 variables, you have a Rosenbrock problem, essentially. 100 variables down here, same thing, nothing changed, except these variables now need to be with n variables instead of 2. And it still works pretty much the same way. Of course, a bit slower, a couple more iterations, but that's still fine. Maybe for 100, 1000 still works. Really quickly worked, as you can see, 900 milliseconds. So thanks a lot for watching. If you have questions about how to use JSO solvers, how to use any of the packages, let me know. Leave a comment down below, and of course, please like and subscribe, and I'll see you next time. Bye-bye.